Good morning, everybody. This is my first attempt at making a video to explain some aspects of chemistry. Let's just see how it goes. It may be a complete fail. I don't know about you, I'm sitting here absolutely freezing in my living room. I've got a dog asleep on the floor beside me who's liable to make woofing noises at any moment. Just ignore him if that happens. So what are we going to do? I thought I would briefly just recap the material that I asked you to look at the end of last term. So that's ionization energy and so forth. And just go over it as a summary and see how you're getting on. So I'm going to pause this while I get the PowerPoint going. So here we are with the ionization energy slide from periodicity 2. That PowerPoint is on the OneNote at the moment. So ionization energy, you will need to be able to write a text definition of ionization energy and a formula definition of ionization energy. So for the text definition, we need to talk about the energy required to remove 1 mole of electrons from 1 mole of neutral gaseous atoms in their ground state. So not in an excited state, in other words. So you need to have the word gaseous in there. And they need to be neutral atoms, neutral gaseous atoms. So when we look at the formula, you can see we have X, atom called X, as a gas, becoming ion X, a negative ion, plus an electron. The second ionization energy obviously refers to removing the second electron, and the values of ionization energy will be different. It may be relatively easy to remove 1 electron, for example, from an element, but the chances are it's going to be harder to remove the second one, and so forth. You can find values of first ionization energy in section 8 of the data booklet. Let's just look at trends in ionization energy. I'm trying. Here we go. It becomes more and more difficult to remove an electron from an atom as the effective nuclear charge increases. And it also becomes more difficult as radius gets smaller. So in other words, ionization energy would increase across a period. And because atomic radius increases as you go down a group, the shielding effect of core electrons builds up because you've got more and more shells, and the valence electrons are further and further from the nucleus, so the radius gets bigger and bigger. So the ionization energy will decrease as atomic radius increases down a group. So in other words, the trend for ionization energy is the opposite to the trend in atomic radius. Let's have a look at this concept, electron affinity. And now you've got to be a bit careful here because electron affinity is defined in 2 opposite ways in different places. So IUPAC refers to electron affinity as energy required to remove an electron from a singly charged negative ion, and it's again in the gas phase. But some people and some textbooks also define it as the energy released when you attach electrons. Okay, so that sort of sounds more realistic to me. If you're thinking affinity as love for, then it sort of, to me, it sounds like attaching electrons. But in actual fact, I believe that the IB regards electron affinity as the IUPAC definition, which is the first one here. So be aware that you know what you're talking about when you describe electron affinity, which way round you're doing it. So in this case, we'd have ion, negative ion X in the gaseous state becoming element X, an atom of element X with the release of an electron. Okay. In the PowerPoint, there are a number of exercises that follow on, which I expect you should be able to do. And the next subject of interest to us is trends in melting point. So here we have a table comparing melting points of group 1 and group 17. We're not going to look beyond group 1 and group 17 in this at this stage, because we need to know more about bonding before we can really look at trends in other elements. But group 1 and 17 bond in similar ways, ionic bonding typically. So we can look at those at this point and make some sense of it. So if you look at the elements from group 1, lithium, sodium, potassium, and so on, you can see that their melting points decrease as we go down the group. Yep. Whereas if we have a look at the halogen elements, fluorine, chlorine, and so forth, or molecules of those, their melting point goes up quite substantially, tenfold in fact, from fluorine molecules to astatine molecules. So how do we explain those trends? First of all, let's have a look at group 1. We said melting points decrease down group 1. And this is because elements of group 1 are metals. And a metal structure, you can regard it as a bunch of positive ions with a bunch of electrons kind of sloshing around. So if you can think of the nucleus and the core electrons being a kind of positive ion, and then the valence electrons don't really belong to any particular atom, but they're called delocalized. So they slosh around and join on and move very easily and join to one atom's electron cloud, and then they jump off to another atom's electron cloud. This is, of course, the reason why metals are good conductors of electricity, because of the ability of their electrons to move from atom to atom. So this is metallic bonding effectively. So the bigger the atom that we're thinking about, or the ion if we like, the bigger they are, then the less the attraction for those outer electrons to the nucleus. So and the less the attraction of one ion for another, if you like. So the whole metallic structure is more easily melted when it's composed of bigger atoms. Okay, we're going to learn more about that in topic 4, but for the time being you need to bear in mind that down group 1 melting points decrease because we're talking about delocalized electrons being less strongly attracted the bigger the atoms become. Now if we look at group 17 by contrast, we know that melting points increase as we go down group 17, and again we need to understand more about bonding to really get this, but enough to say that the forces that hold those molecules together are called London dispersion forces. They're part of van der Waals forces, and the London dispersion forces happen because if you can imagine any atom with electrons whizzing around it, at any one moment more electrons could be at one side of the atom or the other, and so that means that in an instantaneous moment that any atom has got a tiny little dipole potentially. It's unlikely that all of the electrons are going to be completely evenly spaced. So these tiny little temporary dipoles occur in the cloud of atoms, and they hold one atom will attract one little temporary dipole will attract another temporary dipole in the opposite polarity, and it holds the whole substance together. Now these London forces increase when you've got more electrons in a molecule. So bigger elements, that means, have stronger London forces holding them together, and because they've got stronger forces, that means they have higher melting points. So the bigger the molecule in group 17, the higher its melting point. If we look at melting points across a period, you can see quite a complicated picture here in this graph. Generally, the melting points will rise to a maximum at group 14 and then fall to a minimum at group 18. So rising to a maximum at group 14 and then a minimum at group 18. Maximum, minimum. Okay. And this is due to the way that bonding changes from metallic bonding over here to a giant covalent structure. Let's do it through this group, be easier. So we have metallic bonding here to a giant covalent structure like silicon, and then we move to weak van der Waals forces, and finally to just single atoms in the noble gases. Again, this is something that you'll understand much better after we've done chapter 4, so don't stress about it too much for now. But just be aware that melting points across a period are a bit more complex and have these peaks and troughs, which we'll understand better later. So I think that's all for melting points for now. I'm going to stop this recording now and upload it to the OneNote, and hopefully it will be of some use. Who knows? If it only turns out to be useful because it gives me experience, then that's fair enough. But all the best, and see you next time. Bye.